For this problem, we use the fact that the natural angular frequency is given by the square root of 1 over the inductance times the capacitance, which is equal to square root of 1 over. We have 10 millihenries, and we have a capacitance of 25 microfarads. So this gives us about 2.0 times 10 to the third radians per second. And then we can use the fact that the frequency is equal to the angular frequency over 2 pi. So this is 2.0 times 10 to the third rads per second over 2 pi, which gives us about 320 per second, which is the same as hertz. And then once we have the frequency, the period of oscillation is the reciprocal of that, which is 1 over 320 per second, which equals 3.1 times 10 to the minus 3 seconds, or 3.1 milliseconds. Part B. Since the period of oscillation is now known, 1.2 milliseconds, so t equals 1.2 milliseconds, is about 0.38 periods. All you have to do is divide 1.2 by 3.1 and you get this answer. And this corresponds to the following. We want to find Q, right? And we know that the charge as a function of time is given by the original charge times cosine of omega t plus some phase angle phi. And so we know that the charge is maximum at t0. So when t equals 0, q of 0 equals q naught. That implies that q naught equals q naught cosine of phi. So cosine of phi equals 1, which implies phi equals 0. And if that is the case, then q of t now becomes q naught cosine of omega t, and q naught can be given by the relationship of c times the EMF force. We've seen this in the capacitor chapter. The charge is the capacitance times the voltage. So this is 25 times 10 to the minus 6 farads times 300 volts is the voltage. So this gives us a charge of 7.3 times 10 to the minus 3 coulombs. And so q of t now becomes 7.5 times 10 to the minus 3 coulombs times cosine of omega t but we know what omega is. So 2.0 times 10 to the third radians per second times t. So at t equals 1.2 times 10 to the minus 3 seconds, we can say that Q equals 7.5 times 10 to the minus 3 coulombs times the cosine of 2.0 times 10 to the third radians per second times 1.2 times 10 to the minus 3 seconds, which equals minus 5.5 times 10 to the negative 3 coulombs. And if we know the function for the charge, then the current is dq dt, which in this case becomes minus omega q naught sine of omega t. And again, if we use at t equals 1.2 times 10 to the minus 3 seconds, it implies that the current equals minus omega is 2.0 times 10 to the 3 radians per second. The original charge is 7.3 times 10 to the minus third coulomb sine omega, which is 2.0 times 10 to the positive 3 radians per second times 1.2 10 to the minus 3 seconds, which gives us a current of about minus 10 amps. And since we're decaying